It's a great pleasure to be here, and thank you very much for that introduction, Ellen. It's funny to give a lecture at the Dead Sea, and perhaps quantum theory and the conference here can give some life to the Dead Sea. Quantum field theory touches many different bases, and what I'd like to talk about today is a few of these mathematical bases in the quantum arena. So I prepared some slides, and it's a little hard after this lunch to concentrate, I realize. So I'll try to go through these at a level maybe above what's written on the slides. And remind people who are not familiar with quantum theory that the quantum arena is really a Hilbert space. We start with a Schrödinger equation. This is basic to all different forms of quantum mechanics, either non-relativistic quantum mechanics, which was developed in the 1920s, the Schrödinger equation or the Heisenberg equations of motion were studied and found to have very close connection with phenomena that could be observed, especially spectra. And the Dirac equation in the 1930s was an improvement on this, which incorporated special relativity and predicted antiparticles. And at the end of the 1930s, this set of ideas was combined with the idea of a field, namely a field like the gravitational field or other types of electromagnetic fields, other types of fields which describe elementary particles. And the question was how to combine fields with quantum theory. So one tried to express the Hamiltonian and the Schrödinger equation not as a functional of particles and their velocities, positions of particles and velocities, as in ordinary quantum mechanics, but rather as a functional of these quantum fields, which I denote generically with the letter phi. And this led to many different problems, although a pioneering work of calculations and experiments, especially in the 1940s. And I'd like to first mention why people believed and what has made, over the last 50 years, quantum fields a central part of physics, and in fact, also even a central part of string theory. It's closely related to that. But the real belief in quantum fields arose because it described some experiments. And one experiment I'd like to mention is the so-called magnetic moment of the electron. It's a constant, the mu, which describes, when multiplied by the magnitude of a magnetic field, the energy of an electron in a magnetic field. There's a standard unit of this magnetic moment called the Bohr magneton, which is described in terms of fundamental constants, the electric charge, velocity of light, and the mass of the electron. And in the classical theory, the ratio between the Bohr magneton and the magnetic moment of the electron is equal to 1. But the Dirac theory corrected that to 2, which explained a big puzzle in experimental physics. Bush at Columbia University experimentally discovered that the number was not exactly 2, but differed in a small way from 2 in the third decimal place, and the accompanying calculations by Schwinger and others resulted in several Nobel Prizes in physics. But the fact that the magnetic moment is not exactly what you expect because of the interaction between the electron and the electromagnetic field led to a series of calculations and more modern experiments, which probably are, as far as I know, the most accurate experimental test of any number in physics. And the present value, just to show you, is for the difference between the G, which is this proportionality constant for the magnetic moment, in 2 divided by 2, which is the standard way to present it now, is known to all these decimal places And it's in these last two decimal places where there's some uncertainty in the physical numbers. And this is several decimal places more accurate than any spectral experiment, and is a cornerstone of modern physics, and the reason that most physicists believe that quantum field theory is the correct description of nature. Well, most calculations in quantum field theory are numbers that, when they, we heard from V.Milman that there are some things that cannot be predicted at all, but there are others that are predicted to a few percent, some to 10% or 30%. But here is one that people really believe in, and it's sort of at the limit of what can be done either in the laboratory or in calculation. So coming back to the question of whether quantum fields make mathematical sense, this was a problem that arose out of that set of experiments 50 years ago, and which is still not completely settled. The problems arise from two different points of view. One has to do with local regularity, the fact that these are very singular problems, and up to now have required some type of approximation or regularization and a passage to a limit to construct solutions. This local regularity is a very serious difficulty, and we believe this problem, at least I believe, and experts believe that this now can be solved in the four-dimensional world we live in, and I'll talk about that later. There's another question that causes difficulty, and that has to do with continuous spectra in this Hamiltonian, and that often requires a second type of regularization, the so-called infrared regularization, which also can be dealt with now. So what are the fundamental objects? The fundamental objects are this Hamiltonian, and the second most fundamental object is the infinitesimal generator of translations. That's called the momentum operator. So the Hamiltonian generates time translations, the momentum space translations. And this two-parameter abelian group, because these are supposed to be two commuting self-adjoint operators, maps some standard regular domain into itself, and the domain is most commonly taken to be C-infinity vectors for the Hamiltonian. There is an assumption from relativity that the momentum is less than the energy, and that particles have spectra lying on hyperboloids. And this group implements the translation, the space-time translation, all objects that are studied in the theory, and in particular the fields themselves. And because the unitary group has a regular domain, there's also the field itself, which is, as Jörg Froelich pointed out, an operator value distribution. However, what this means is that expectations of this field in vectors belonging to this regular domain are actually smooth functions, C-infinity functions of space-time. So the field itself is a very nice object from this point of view, and you don't see these local singularities once you have the Hamiltonian and all the structure, namely the Hilbert space on which these operators act, the Hamiltonian, the momentum, and some time zero field. The real problems begin to arise because you want some additional structure. You want the field to satisfy certain very important relations. And the first property that you'd like is the so-called canonical property, which is the generalization of the Heisenberg or Boyle relations from a finite number of degrees of freedom to an infinite number of degrees of freedom, namely the Fourier components of the field. And what you would like is, at a given time, for the field to satisfy the so-called canonical commutation relations, namely the commutator of the field on its space-like hypersurface with a field, the time derivative of a field, and I've written down this relation for so-called bosonic or scalar field, should be proportional to a Dirac measure, and there's a square root of -1, which is a standard quantum mechanical object at h, which I've set equal to 1, rather than c, which Jörg Froelich set equal to 1. And this, what? Oh, maybe you said h equal to 1, so I've said h equal to 1 too. And I've written here this corresponding relation for fermions, which involves an anti-commutator. But it's clear if this relation is going to be satisfied, or even after so-called renormalization, where there's a constant introduced into this relation on the right-hand side, there's singularities which could cause problems if you try to multiply fields together. And it's these singularities that are at the cause of the difficulty, because you not only want this canonical property, but you want the fields to satisfy some nonlinear differential equation of physics. And this is the defining equation of physics. If you have a linear equation, if this potential function, this nonlinear function of the field is 0, there's no difficulty. You can write down the solutions very easily by Fourier analysis and analyze them in complete detail. But in the theory of quantum fields, that's a non-interesting case. It's the case that describes particles that travel in straight lines and don't interact. And the interaction is all contained in this function v. So this is like in Newton's equation, the wave operator is equal to the derivative of v. It's the gradient of v, if it has several components. Or there's some variational equation. This indicates there's a variational equation. Now, so the source of the difficulties technical difficulties come from combining these types. And this leads to what physicists call renormalization. In order to make this equation well-defined, the nonlinearity is treated in a way where you regularize it and pass to a limit. But in passing to the limit, you often introduce constants that diverge as you pass to the limit. But mathematicians are very familiar with this phenomenon, because in defining the derivative, you also take the difference of a function at two different points and divide by the distance and let the distance tend to 0. So if you try to analyze the individual terms in the difference, it has no meaning, but the difference itself tends to a limit. Now, there are two. In the later part of my talk, I'll show you an example where actually there are no infinities. If you look at the individual parts of the problem, you'd think there were, but they cancel each other out because of the algebraic structure of the problem. So these problems have a strange property that they tie together analysis, algebra, and as I'll mention in a moment, probability theory, but also geometry and topology and even number theory will rear its head, and I'll get to that before the end of my talk. Well, there are two fundamental methods that have been used to study these questions. And the first is probability methods. That they're based on integration over function spaces. And these probability methods are very convenient because on a probability space, it's easy to define partitions of unity, it's easy to define expansions, and it's easy to work and prove estimates using LP spaces and all sorts of inequalities, which are classical inequalities that come up. Like any problem in analysis, these problems in quantum field theory require space being divided up into small bits, and actually phase space being divided up into small bits and analysis done on each bit, and the problem being pieced together. But we also want to get back to the Hilbert space, which, because of the interpretation of space-time, gives rise to phenomena like finite propagation speed. There's questions of locality that's connected with finite propagation speed. Two points that cannot be connected by a light ray will fields at these 2 points commute like the initial data that I wrote down, or anti-commute in the case of fermions. And questions of geometric invariance often have very simple expressions when looked at from the point of view of Hilbert space. And nice theorem connects these two methods. It was established some time ago. In the ordinary quantum theory, it comes out of the work of Feynman and Mark Katz, known as the Feynman-Katz formula, where expectations of a heat kernel in Hilbert space are given on the right-hand side by some probabilistic integral, or integral over function space. This has a number of beautiful generalizations which pertain to quantum field theory, namely systems of fields or an infinite number of degrees of freedom. Kurt Zematzig, a very deep German physicist who died prematurely, and Ed Nelson are responsible for posing this in the form we use it now. And the relation that's most convenient and applies in the widest variety of circumstances was discovered by Osterwalder and Schroeder in the 1970s to connect these two. And in fact, Osterwalder and Wisniewski extended this construction to superspace and supersymmetry fairly recently. And this cornerstone of, in fact, I feel it's some connection that should be in every basic physics books on quantum theory, and there's not in very many of them, is a very important thing. So once you have these two methods, and I might mention that most mathematicians think that function space integration is something only formal, namely that there's not a complete mathematical theory behind it. It's actually true that in most cases that physicists write down, there is not a mathematical theory. But there is a very useful mathematical and widely applied theory that will pertain to the examples I'll discuss, and which in this context gives the precise connection between the right and left-hand side of this formula. So to begin, I just wanted to list a few of the early existence theorems. Existence is the first question, which, using these methods, have been proved. And I made a list. I won't go through this in detail, but D is the dimension of space-time, which I've written as some space manifold across R. There may be some more complicated structure, and we will see that in the examples I'll write down later, but I'll write it in this form. And the important thing is that these problems get harder as the dimension of space-time gets larger. But basically, in 2- and 3-dimensional space-time, these problems are pretty well understood. And in fact, if you take the manifold M to be compact, one set of examples, you need another set of tools to go to non-compact manifolds. But there has been a technology developed where in 1965, even the simplest problem was thought far beyond the reach of actual mathematics. That problem looks very easy, can be done on the back of an envelope compared to the 3-dimensional problem, which, in fact, I regard this as the most complicated paper that not only that I've been involved with, but that I know. So,
do you mean relativistic theory or non-relativistic?
Yes, these are relativistic theories. So they're first constructed often in a finite volume and then passed to a limit, and they're totally relativistic. Special relativity, not general relativity. Now, it's interesting that, for instance, this three-dimensional work, it's done by a phase cell analysis where phase space is chopped up into small regions. You have to go to somewhere near the limit of the uncertainty principle and how small you make phase cell boxes, and then show that different regions of phase space are independent in some quantitative sense. But what the point I wanted to make was that while there have been other methods, the so-called renormalization group method, which is an iterative method and embodies many of the same ideas as the phase cell localization method, systematizes these expansions to make them iterative. But based on the renormalization group method, there, as far as I know, isn't a complete proof of these results.
The existence of what?
This is the existence of a Hamiltonian, a momentum, representation of the Lorentz group, and a quantum field. And if you want to formulate it precisely, you might say satisfying something. There's a set of conditions that a quantum field have to satisfy abstractly. That set of conditions goes under the name of axioms. There are a couple of different sets of axioms. The Hogg-Kessler axioms, which concentrate on the algebraic structure of the quantum fields. This was mentioned in Jörg Froehlich's talk and Alan Kahn's talk. Or the Whiteman axioms, which concentrate on the Green's functions of the quantum field. And they're related to Green's functions after analytic continuation to imaginary time by the Osterwalder-Schroeder axioms. Well, these examples I've listed here satisfy any of these axioms, and various papers listed here and other papers have established that. The fields then satisfy these appropriately defined partial differential equations that are connected to the Lagrangians that describe them in various different ways. But I don't want to technically describe the theorems. It would just take more than the time I have in my lecture. But essentially, it's a complete solution of the existence theorem for the problem.
And what about spin? It's a scalar fields or?
This applies to all the results are basically for scalar fields and spin 1/2 fields. There's some photon fields have been dealt with in some special cases.
Does this mean that you have method of supergravity is out from that?
Well, these are the early results, and 11-dimensional supergravity. Nothing has. I mean, the borderline that we're at here for these methods is 4 dimensions. Nothing in higher dimensions has been done. Oh yes. Oh well, that's very important. Thank you for reminding me. Greater than 5 dimensions, for the simplest example, and that's the Cordic wave equation, where this potential is just the 4th power of the field. So the energy is called 5 to the 4th. It's a very important result that in 5 or more dimensions, if you make a number of reasonable assumptions about the approximation method that you use to modify the problem, the basic one is to put space-time, replace space-time continuum by a lattice, and then take the limit as the lattice spacing tends to 0. These equations in 5 or more dimensions with this potential are so singular that the only way to define the nonlinear term turns out to be 0. That the nonlinear term, there are interpretations of this result in terms of the intersection of random paths. And there is some formulation of quantum field theory where the interaction in this example can be described in terms of the intersection of 2 Brownian trajectories in 4 dimensions. Now, we know that Brownian trajectories have a Hausdorff dimension 2, and above 4 dimensions, they don't intersect typically. Below 4 dimensions, they intersect, and you could say that that explains, to some extent, the reason that you can prove existence below 4 dimensions. And 4 dimensions is a borderline case, which is very difficult to analyze. Well, Jörg-Froelich established in 1982 a non-existence theorem in 5 or more dimensions, and Michael Asman independently did some related analysis. And this is all based on a lot of other work, and in fact inspired, I believe, by the picture Kurt Szymanczyk's. So
nothing is known in 4 dimensions. Nothing is known.
Nothing is known. So my first question, and that's, Sergey, for you to work on. Do Yangmills, SU2 Yangmills fields exist in 4 dimensions? And I compactified space. And actually, there are partial results here that indicate that this problem can be solved. There was a breakthrough by Thaddeus Balaban in 1985, and there's some independent work by Feldman, Mannion, Riverso, and Senor, but this is much harder to understand. In fact, I've never met somebody who's completely understood this work because it's not explained in a way that's consistent with modern mathematics. But the work of Balaban is really beautiful and goes a long distance to proving existence to the 4-dimensional Yangmills fields. I might just mention as an aside, without trying to explain it, that there's a reason that we believe, a heuristic physics reason, we believe the quartic scalar field theory in 4 dimensions has no solution. That is, that the result of Jörg-Froelich, which, if you make some assumptions, also applies in 4 dimensions, actually puts a nail in the coffin of the 4-dimensional equation. That's based on renormalization analysis. If you believe this renormalization analysis, which is an extrapolation of perturbation theory, then the equations have no solution in 4 dimensions. However, there could be a non-perturbative type of solution that exists, and so that's open. But it is a very subtle phenomenon, and certainly I believe it's much easier to prove that the 4-dimensional Yangmills theory, which doesn't, has the property which physicists call being asymptotically free, and therefore well-behaved in perturbation theory if you can understand the large field phenomenon. The techniques have been developed, but actually it's at the point where the work of Balaban has to be redone from scratch because it was not done in a sufficiently general context to take the limit and to analyze this problem in complete detail. So it's really a piece of work waiting to be done. It's very complicated, but it looks extremely promising. And if you do solve this problem, you've solved a 50-year-old problem of the existence of 4-dimensional quantum fields. Yes?
Perhaps for the outsider, you could just tell us the importance of the power 4, or is that just the beginning of any power? Why are you looking at power 4?
Oh, the power. These are Yangmills, so this is not.
The previous slide.
Oh, the power 4 is the least singular because if you can think of the difficulty arising from the singularity, then you want a polynomial that's the lowest degree. Power 2 is trivial. That's power 3 doesn't have positive energy because pi cubed gets negative.
No, but there's another reason.
Supercritical or something?
It has the same scaling as Yangmills.
Yes, it has the same scaling as Yangmills, but it doesn't have the asymptotic freedom property. And therefore, the asymptotic freedom property makes it much easier at a level of resummation of perturbation theory. And so this looks like the easiest example.
If you look just for classical Yangmills fields for gluons, and what's known about the existence and uniqueness of the classical equations for...
Well, there's lots known, and Weinerman sitting next to you is the biggest expert on this problem, so I think I'll defer to him because I have a lot of other things I want to talk about. Maybe we could have that in the discussion session. Okay. Now, for the second problem, has to do with some more detailed structure, the spectrum of the Hamiltonian. And I'd like to talk about the spectrum of the Hamiltonian restricted to p equals 0. Since h and p commute, we can simultaneously diagonalize these two operators. And there are two qualitatively different situations. One situation where there's a gap in the spectrum, and that's described here. There we have structure in terms of particles, and the energy is generally normalized, so the minimum eigenvalue is defined to be 0. And if there's a gap, and in fact, in the examples I wrote on the first slide, in many of them, there's proved to be an isolated gap, where this is an isolated eigenvalue of h restricted to p equals 0. And this is a very subtle and difficult theorem, but true. And then a continuum starting at twice the value of this eigenvalue. And the reason that the continuum starts at 2m is that this eigenvalue has the interpretation of a single particle of mass m. And when you have 2 or more particles, they can have a relative momentum, and therefore there's a continuum starting at 2m. And there may be other states, like this possible bound state here, which would lie below 2m, and may or may not be there, depending upon whether the interaction is attractive or repulsive. Now, the other situation is no gap. And in fact, a gap is more or less forced in the examples that have been studied in most detail. In many of the ones on the existence transparency, by starting with a theory with a gap and perturbing it by the potential. And this is, let me go into that in a little more detail. So if I start with a quadratic polynomial phi squared and perturb it by some higher degree polynomial v1, and I want to preserve positive energy, so v is bounded from below, then the theorems, the general expansion methods, and show that for lambda sufficiently small, there's a gap. And the gap which is present in the trivial way for lambda equals 0 is just preserved, and this isolated one particle state is there. The bound states may or may not be there, and in fact, for this quartic wave equation, a quartic potential cubic wave equation, there's no bound state. It's known that the theory is repulsive. Well, if you take phi 6 minus phi 4, it's known to be attractive. And this is very beautiful work done by, well, I was involved in the repulsive cases, where a number of other people, Dimmick, Spencer, Zerilli, Ekman, were involved in showing the existence of the bound state. And there's a big literature. But what happens if lambda becomes large? There's a critical value of lambda where the gap goes to 0. This is called the onset of phase transitions. This is also qualitatively known. And it's a beautiful piece of work which I'm not going to describe in great detail. And then as you increase lambda again and make it very large and positive, a gap appears again. And in fact, you go back to a classical theory which, with a quantum version of a classical theory that has 2 ground states described. There's a reparameterization which makes, in the quartic case, the potential have this form. And for very large lambda, you can again get very accurate expansions about that potential. So a lot is known about these problems qualitatively, aside from existence. And I can't go into this in great detail, but then ask this question, which is a very fundamental one. Does Yangmills, which without the interaction has no gap, it describes zero mass particles, does Yangmills have a gap? Now, this is a really interesting problem, both from a mathematical point of view and a physics point of view. Of course, I said that we want to prove the existence of 4-dimensional fields. Well, you could look at 3-dimensional Yangmills fields, or look at gaps that are uniform as you remove the approximations in 4 dimensions. And the reason one is interested in this is that actually major problems in physics would be solved if this were known to have a gap. It's believed by many physicists to have a gap. In fact, it's so well believed that many people just take it for granted there's a gap and think that it's a stupid problem to study. In physics, it's known as the problem of confinement or core confinement. And yet, where would the gap come from? Well, the Yangmills curvature is the differential of a connection A plus A cross A, if we look at SU2, that A lies in the three-dimensional Lie algebra. And the Yangmills action is the square of this, proportional to the square of it, and involves this chordic potential term. So the gap could arise because this chordic potential is large for large A, and therefore confines the states of the theory for large A, but there are certainly flat directions. And the question of whether this has a gap or not is not understood at all. Richard Feynman, shortly before his death, wrote a paper where he proposed a way to see that this theory did have a gap, but that idea has never been fully realized, and physicists don't have a heuristic solution that I know to this problem either. So this is a really interesting and difficult problem, and I mentioned it. So my time is running, and I'd like to mention something about supersymmetry, because I did say that the relation of theories with both fermionic and bosonic types of particles is of great interest, and in fact connects up now with the world of geometry. So in the supersymmetry really can be described, I'll describe it today, by finding a Dirac operator which is related to the Hamiltonian and the momentum by a square root. Namely, the Hamiltonian and momentum are each given as the integral of a density. And we want to look for another operator which is the integral of a density, but odd under a certain Z2 grading, that grading being -1 particle number, and whose square is related to the energy and momentum. Often you say that supersymmetry is the description of an energy that has a local square root, but I'm going to say Q squared equals H plus P. This is a special type of supersymmetry. And in fact, you might expect a second Q whose square is H minus P in our two-dimensional problem with space given by a circle. And here we have our grading. Now, the reason this is nice for mathematics is that it connects into index theory. And I can define the partition function of this system as the trace of the grading times e to the minus h. And if this Hamiltonian, and the charge Q, or this Dirac operator, which is Dirac operator in loop space, depends on a parameter, it's very and P does not, then if the dependence of on the parameter is sufficiently regular so you can differentiate Z is, as a consequence, constant. And the argument is a standard argument in index theory, but I'd like to repeat it for people who are not familiar. So if Z is differentiable, it's constant. And so let me prove one thing in this lecture. I'll calculate the derivative of Z. To do that, I need to calculate the derivative of H. H is Q squared minus P, but P does not depend on the parameter. So the derivative with respect to Q squared of Q squared with respect to the parameter is Q dot plus Q dot Q, where Q dot is the derivative of Q. And therefore, we can differentiate the exponential trace gamma e to the minus h by bringing down minus sign and bringing down the derivative of h. Because this trace is cyclic, I can rewrite the terms in this order, and I'm going to assume that the differentiation is sufficiently regular so I can use cyclicity of the trace. This is actually a very important fact I'll come back to. And then, since Q is odd in the degrading, if I move Q to the left through degrading gamma, I pick up a minus sign. And then by cyclicity of the trace, I can move Q around to the right in the first term and bring it back through H, because Q commutes with H, as Q is translation invariant, commutes with P. Oh, I'm sorry. So I do a simple calculation. I have the derivative here. I look at the first term of the derivative. I bring Q gamma equals minus gamma Q, so I pick up a minus sign in the first term. And now I use cyclicity of the trace to bring Q around and through H back to the right, and I have the negative of this term, so the two add up to 0. So the derivative is 0 and the function's constant. This is an invariant. Well, that's all nice and good. However, typically, this is piecewise continuous, and it jumps. And you often want to evaluate this function at an endpoint of some interval where it's very tricky to see whether or not it jumps. And if it didn't jump generically, all indices would be the same, and this argument would apply. So you really need some analysis, but this is a fundamental idea and can be used not only to study this index, but also an equivariant index. Now, I'd like to just mention one particular example, and this will be, I'll give an example of understanding endpoint regularity where you can prove this differentiability on an open interval, but then you want to understand what happens at the endpoint. And I'm going to look here at a slightly more complicated example, which involves the type of group that Alain talked about yesterday. Here we have a translation and a twist. So we'll have a two-parameter group acting on our fields, which give a twist and a translation. And look at a Hamiltonian that commutes with that group, so we can take the trace not of e to the minus h, but we're going to introduce a parameter beta, a real parameter, positive parameter in front of h. And this is the space translation parameter and the twist parameter. And this partition function is called the elliptic genus, and the same argument about the constancy in a parameter applies to this as it does in the proof that I gave. And so here, there's a physics expression for this Q, and a variety of examples parameterized by polynomial potential V. I'll just write down a formula to show that it's there, but and then I'm going to take for my parameter lambda just an overall multiple of this potential, where Q is this potential, the gradient of the potential now in some direction of the scalar or bosonic field multiplied by a fermionic field. And that provides this Q operator plus the Q for lambda equals 0. And I'm just going to assume that the V sub j, that's the component of the gradient, is a holomorphic polynomial of degree n tilde. And this gives rise to Hamiltonian, which is of a Yukawa type. It's called a generalized Yukawa potential because the interaction is the standard Yukawa. It's also called West-Zumino or Landau and Ginzburg because it's also the type of, for cubic V, it's the type of Hamiltonian that was used by Landau and Ginzburg in solid-state physics, and West and Zumino in their discovery of supersymmetry. And Yukawa for cubic V then is second derivative of v is linear, and this is what's in physics called the Yukawa equation. Anyway, I'm going to just quickly make two assumptions to make this mathematical. One is that v is a quasi-homogeneous polynomial. Quasi-homogeneous means that there are some constants which for a homogeneous polynomial would all be equal, so that the gradient component of the gradient times the coordinate times that constant adds up to the original polynomial. And I'm going to assume that the polynomial has degree at least 2, so the constants lie between 0 and 1/2. And then we need some elliptic bounds on this polynomial. And I don't want to go into that in detail, but these elliptic bounds are necessary to make the whole theory work. So then, with this example, there's a theorem about the endpoint that the z is differentiable for lambda between 0 and 1, and Holder continuous with a very small exponent at the endpoint. Now this Holder continuity at the endpoint is absolutely crucial because it rules out the possible jump in z as a function of lambda. And it's quite subtle to establish it, and the Holder exponent is proportional to, almost proportional to the inverse degree of this polynomial. Well, to actually prove this, you need a number of sophisticated estimates, a priori estimates, and there are versions in quantum field theory that are analogous to some things that Jörg Krolik talked about in his lecture. I mentioned a couple of the estimates here, but I don't want to go into them in detail because that's some analytic details. But for instance, this estimate is an infinite dimensional Gordian inequality. This estimate is another similar type of inequality. And then we have some inequality on the trace of the heat kernel to make sure it's trace class for all. And this. Pardon me?
What is the measure? If you win a measure, when you say infinite dimensional, so you can go use some measure.
Yeah, well, it's something like the Wiener measure, but it's not the Wiener measure. It has, well, something like that. Yeah. So the amazing thing is then, as a result, there's an actual formula for the answer. This thing can be computed in closed form. And the formula involves these Jacobi elliptic functions. So Don, you might be interested. It involves the potential only through these weights of the quasi-homogeneous polynomial. Namely, the partition function up to some multiple is just a ratio of Jacobi elliptic functions where the first parameter is the space plus imaginary time. And the weights enter here, and theta is this twist angle. And then there were two, I guess I didn't explain what phi is. That's another twisting angle. And if we take phi of x plus a period, we get back to e to the I omega little phi of x. And that's this angle here. So this shows that equations without any conformal symmetry, these general Yukawa equations, have a hidden conformal symmetry because this partition function is a modular form. In terms of these variables, it has the standard transformation property of conformal SL2Z symmetry. Now, in order to prove that, there were heuristic things like this in the physics literature, but it's absolutely essential to establish these a priori estimates in order to show that this function is what I've written down. And in fact, this formula, as I've written it down, is new. But the limits are very non-uniform because, for instance, if you take the limit as phi tends to 0 and q tends to 0 in opposite orders, you get very different limits. One being an important index in the problem, and the other being 1. So it's really important to have the analysis straight. And so question 4 is, I didn't want to go into that in such detail, but just to guess question 4, to get to this hidden symmetry. How can one exhibit hidden symmetry without explicit forms of the invariants? Here we see the hidden symmetry because we discover that the invariant is a ratio of theta functions.
So before in physics, would that mean you have conformal field theory as well?
That's true, but this is not conformal. It's far from conformal. And this is an invariant in something that has no conformal, obvious conformal nature. And this is hidden. And so my question is, how do you find the hidden conformal symmetry? Is there some underlying principle that leads you to this hidden symmetry? And this is just one example. There are other types of symmetries, the mirror symmetry, duality symmetry, which it would be very nice to have a way to look at the problem and to understand right at the beginning that that symmetry should be there. Well, I have another section on non-commutative geometry, but I think Alain dealt with that. Let me just say, ask the question number 5. Does non-commutative space regularize quantum field theory? Well, this particular example I spoke about, the West-Zumino or Landau-Ginzburg quantum field theory on a circle, is actually finite. I didn't have to write down renormalization when I specified Q, even though if you looked at it in detail, you might think that infinite renormalization is there, because the algebraic structure relating due to the supersymmetry that relates the bosonic and fermionic parts of the problem exactly ensures cancellation of the singularities. Well, to what extent this is generic is not known. Physicists believe that supergravity was finite for a time and didn't seem to turn out that way. But the twist that I put in is like the phenomena that occur in the quantum space, and so it's possible that quantum field theory on quantum space is actually more regular than quantum field theory on flat space. And this twist, this angle phi that I put into the problem I just described, actually regularizes this problem. And if I tried to construct the example with phi equals 0, it would not be possible without introducing some other type of regularization. But that would have destroyed this symmetry, this hidden symmetry. And therefore, it was very nice. This drove me to use this regularization method, which doesn't destroy the hidden symmetry. Instead, it destroys supersymmetry partially, but not completely, and that's why I concentrated on the Q that I described. But the question is, what Alain said in his talk he would like to have some new physics or new mathematics come from non-commutative geometry. I'd also like to see new physics. There are many ideas that mentioned in the earlier talks that connect ideas in string theory with non-commutative geometry. And it's isolating one of these and bringing out the importance of it in a concrete problem that perhaps is the real essence of question number 5. So I've gone over time, and I'll stop. I just had some main principles here. There's mathematical functional integration. A priori estimates are essential. They're not useful, they're essential. Symmetry and invariance give great insights, and what is the meaning of symmetry in a deeper sense. and you can't get away from phase self-localization. So I hope we'll have a lot of questions for the discussion. Thanks.
Arthur, may I ask you the following thing? What does it mean to quantize Ginzburg-Landau system? It is by definition Ginzburg-Landau after superconductivity theory is just equation for the anomalous Green function. It does not, you cannot quantize it at all if it is really the same physical system. That is, or it is just informal terminology.
That's an informal terminology. What I mean by that is just to study a particular Hamiltonian that depends upon a scalar and a fermionic field. And the form of the Hamiltonian is the Hamiltonian for a linear system plus a bosonic term, which is the gradient of the potential function of the field squared. And then there's an interaction between, so this for a cubic V has the Landau-Ginzburg form, and then there's a cross term that has the form psi or psi and the Hessian V plus its adjoint.
But this is a scalar, this is a real field, but the Landau-Ginzburg is a complex field.
This is a complex field. So phi is actually takes its values in Cn.
But it should exclude
It's just quantum field theory, but that's
It's a quantum field theory of
not
physics.
really Ginzburg-Landau, but
No, it's a field theory of physics. Ginzburg, classical Ginzburg-Landau theory.
Okay, so maybe if you want to ask a question, maybe you should ask it now. And Arthur will not answer immediately, but at least we remember for the discussion session. Or at least try to remember it for 1 hour.